So it's my vector field is x, z, minus y, and that's by I always run out of room when I, J, K. And so the first thing I'm going to do is I'm just going to use the sort of the standard relationships between Cartesian and cylindrical, because the first one I'm going to find is the vector field is a cylindrical vector field. And so that's sort of my usual x is equal to rho cos phi, y is equal to rho sine phi, and z is equal to z. So that's the standard relationships that we're talking about here. So rho cos phi z, it's just z, and then minus y minus rho cos phi. And then to convert it into cylindrical, we take this IJK column matrix and we replace it with this here. So have cos phi.
Sorry, is y meant to be negative rho sine phi?
Yes, thank you. Thanks. And then it's minus sine phi cos phi 0. And remember the 1 is in that bottom right-hand corner. And then, so we're converting it to sort of those, so univector in the rho direction, the phi direction, and the z direction. And then we just use matrix multiplication to expand that out. So rho cos phi by cos phi, so we get rho cos squared phi by z plus z by sine phi, z sine phi, and then minus rho sine phi by 0, so there's nothing else there. And then we do it, again with the second column, so we get minus rho cos phi sine phi plus z cos phi, and then the last one we just get minus rho sine phi. And so therefore we've got the cylindrical vector field as a function of rho phi z is going to be equal to rho cos squared phi plus z sine phi in the direction of rho, plus I've taken out a common factor of cos phi here, z minus rho sine phi in the direction of phi, and then minus rho sine phi in the z direction. Does that make sense to everyone so far? And then we're going to do the same. So we're going to do the same again. Except this time we're going to use the standard relationships between Cartesian and spherical coordinates. So you get x is going to be equal to r sine theta cos phi.
Catherine,
Yes.
I multiplied the unit directions by the rotation matrix first, or whatever it's called. I don't know if it's a rotation matrix or whatever, and then multiplied it by the XYZ matrix, if that makes sense. Is that okay?
I mean, if you're going to get the same answers, yes, that's okay. I can't quite.
Yeah, okay.
Do you mean like you multiplied xy minus y by this matrix here?
I
And
multiplied the the E matrix or the E matrix by
yep.
so I got the cos sine matrix and multiplied that by the E matrix. So left to right, like how you wrote it,
You
but
might
I
have
did
to
that.
if you send me like an email with what you've done, I can
Okay.
give you. But at the moment, I'm a bit confused by what you're doing.
Yeah,
So
okay.
I'm gonna continue.
Yeah.
Um, okay. I think they were older comments. So, and then what y is r sine theta sine phi, and z is r cos theta. So we get r sine theta cos phi, r cos theta, minus r sine theta sine phi, and then we've got to use this matrix here this time. So what's that? Sine theta cos phi, sine theta sine phi, cos theta phi, cos theta cos phi, cos theta sine phi, minus sine theta 0 cos phi minus sine phi. And then we just do the same thing. We need to sort of multiply that out. I mean, if I multiplied this matrix together and then this, and then I multiplied this by whatever the result was there, that's not going to matter. But yeah,
Yeah, that's what I
if
was
you,
doing. Like
I
all the sine cos stuff, multiplied that by the E stuff, and then that answer on the right hand side of all the variable stuff.
yeah,
I wish my maths language was better. I'm sorry.
it's okay.
Cool.
I don't think it should matter, but
No, just as long as the matrices are in their order,
yes,
it doesn't matter if you do the right hand two first and then, yeah.
yeah.
Cool. Awesome. I'm happy about that. Thank you.
No worries. So if I multiply this out, So these two terms cancel. And then the next one is going to be r sine theta cos theta cos squared phi plus r cos squared theta sine phi. Oops. This one here is actually the theta unit vector. Sorry. And so I can simplify that and I get because this cos squared theta, sine squared theta, they're just going to sum to 1. So that's where I get that from. And I think I've just taken out a common factor there. And so that is equal to the vector field in spherical coordinates. Did anyone have any questions about that at all? The next part of the question, we're going to compute the curl of the vector field now in Cartesian, cylindrical, and spherical forms. So the curl in Cartesian is simply, so I don't think you've been given the Cartesian form of this, but it's pretty simple. I'm sure you've your lectures notes.
Tons of times.
So, yeah. I figured as much. So, in fact, I'm not going to write it out again. So my F1, F2, and F3 are, so because my vector field is xi plus zj minus yk, it's going to be x, z minus y. And so then it's just the determinant of this matrix. So if we differentiate minus y by y, we get minus 1. Differentiate z by with respect to z, we get 1, so minus 1 I. And then these ones, everything else is going to sort of be 0 derivatives. So the curl in Cartesian coordinates is minus 2i plus 0j plus 0k. And then in cylindrical coordinates, And then so it's F1, row F2, F3. And so in cylindrical coordinates, we want to use what we found here. So it will be, this is my F1, this is my F2, but I need to do row F2, and this is my F3. So I haven't left enough room. I made the same mistake in my workings before. You'd think I'd learn. Um, and I actually expanded it out here because it's easier then for differentiating. So you'll see that I added that row, an extra row term there, and don't forget about this row term here as well. So if we differentiate minus rho sine phi by phi, we get minus rho cos phi, and then we're going to take away this, like if we differentiate this middle term here by z, so the only z is here, so that's minus rho cos phi. And then we've got minus rho, so that's that row there, and we get minus sine phi, and then we differentiate this first term here by z, so minus sine phi. And then the final term is we differentiate this by phi, so we get z cos phi minus 2 rho cos phi sine phi. I'm not sure what I said there, but we're differentiating by rho. I think I might have said phi. And then we differentiate do you mean this sine phi here, Oliver? It is negative because it's minus yeah, cool. And then it's minus this first term differentiated with respect to phi, so we get 2 rho cos phi negative sine phi, so I put a plus there, and minus z cos phi. So if we simplify all of these and take out, multiply everything by 1 on rho, we get minus 2 cos phi in the direction of rho plus 2 sine phi in the direction of phi and plus 0 ez. which we're expecting because that z is the same up here. And yeah, those terms all sort of cancel out. And then we can do the same for to find the spherical curl. So again, we need to use the f1 will need to be this term here in spherical coordinates, and then this is our f2 and this is our f3. And I think I'm just going to skip the working on this one and just give the answer if that's okay. Because otherwise I'm not going to get through everything. But here is the answer if you want to go work through it yourself and check your answer. Did anyone have any questions about that part of the question at all? I'll move on to question part 3. And so now we want to use what we found for the curl to compute this integral over each of these surfaces, which I've defined below. I'm not going to do 3 surfaces, but I have sort of set out 3 surfaces anyway. So we've got a sphere of radius 4. We've got this red line traced out here. I think, and that goes that way around the circle. And then we've sort of got 3 surfaces that are bounded by this this space curve, and we're going to compute this integral over the surface of the curl by the normal vector for each surface. So I'm going to start with this black surface here. So it's just a disk. So you think, I've got a disk, constant z, perhaps cylindrical coordinates would be the best. So I'm going to use that what we found in part 2, this form of the curl here, and so this was the answer for that there. So my surface 1 is given here, and so my normal for surface 1 is going to be given by it's in the direction of Z, pointing upwards. And I chose that direction because I think if you go on and if you use the right hand rule and the direction of the space curve is sort of that way, that's the direction of the normal vector. And so then we need to find the curl in cylindrical coordinates dotted with the normal vector for surface 1. And so if we recall, that was minus 2 cos phi e rho plus 2 sine phi the direction of the space curve, I because in part 4 you're given the parameterization for it, and so if you trace it out as t increases, we go around that way, and you can work that out by just if where am I at t equals 0, where am I at t equals pi on 2, etc. So make sure you use the right vector, and we're dotting that with just e to the z. I'll just zoom out a bit so I can. That looks a bit weird going on to the next line. And so, the normal vector doesn't have components for rho or phi, and the curl doesn't have anything for the direction of z, so all I get when I dot them together is 0. I can I'll give you a hint for your assignment. Your answer is not 0. So therefore, when I integrate over the surface 1, it's quite easy in my case. It's not going to be as easy as yours because it's not 0, but it's still not a difficult problem to solve. So I just get 0 here. And so, and if I do the same for surface 2, which is, so surface 2 is this orange sphere here. And so the normal vector is going to be pointing outwards, whereas the normal vector, and so that will be E R. This one will just E Z. But for the green surface, you'll find that the normal vector is pointing in. So that will be minus E to the R. And so surface 2 is this spherical shape. So it makes sense to use the curl in spherical that we found in spherical coordinates instead. So if we go the curl of the vector field in spherical dotted with the normal vector for the surface 2, we get, so that one was the one I didn't show you all the working for, but it was minus 2 cos phi sine theta plus, actually it's minus 2 cos theta cos phi e theta plus 2 sine phi e phi dotted with ER. So minus cos phi sine theta. So now, again, I'm going to integrate over the surface, this time surface 2. This time, it might be helpful. Maybe mine was 0 here, but it could help you that you'll need ds rho, d rho, d phi. Whereas here in spherical coordinates, I'm going to use ds is r squared sine theta d theta d phi. And we're doing that at constant r because the radius is 4. So theta's going from 0 to 2 pi on 3 because we're starting from the top angle here and we're going all the way down to 2 pi on 3. And so this would be theta is equal to 0 and this is theta is equal to 2 pi on 3. And we need to integrate sine squared theta. So this 32 came from subbing in r equals 4. And then phi is going to go from 0 to 2 pi because we're going all the way around here. So that's cos phi d phi. So I've used the like this formula for sine squared theta. But you should find that this part of the second part of the integral is going to, because if sine 2 pi is 0 and sine 0 is 0, so this goes 0. 0 minus 0 is going to be 0. So we're going to get 0 again. And if you did it for surface 3 as well, you're going to get 0 as well because even though they're different surfaces, we've got this it's the same, they're sort of bound by this same path here. So then the last part, I guess, is showing, like, if we convert the line integral, we're showing that that's equal to those surface integrals, which is why they have to be the same and equal to So you can do this a few ways, but I've chosen to do it like this. So if my RT is given by 2 root 3 cos ti plus 2 root 3 sine tj minus 2k for t from 0 to 2 pi. And then I can find dr dt. So that's minus 2 root 3 sine t I plus 2 root 3 cos t j plus 0k, because the 2 is just a constant there. And then we also want to find the vector field when we sub in sort of this parameterization here. So that would be xt I plus zt j minus yt k. So x of t was this 2 root 3 cos t I minus 2j minus 2 root 3 sine t k. So then we want to find this dotted with this vector here. And we're hoping that we find that our answer is going to be 0, as we found before. Oh, sorry. We want dr dt. I was doing rt. So sorry, so we'll get the minus 2 root 3 sine t plus 2 root 3 cos t j plus 0k. And when I dot those two together, I get minus 12 cos t sine t minus 4 root 3 cos t. There's nothing from the last one. So therefore, when I find this line integral here, that's going to be equal to, I'm going to take a common factor of 4 out the front, and I'm going to go from t equals 0 to 2 pi, and it's 3 cos t sine t plus root 3 cos t dt. Because we're fine, so this f dot dr is equal to what we've the f of r of t dot dr dt dt. So that's what I found. So when I integrate that, oh, sorry. And as before, you can see we've just got sine t's, and we know that at 0 and 2 pi sine t yeah, t equals 0 or t equals 2 pi, sine t is just, they're all just zeros. So we're going to get that equals 0. And so we've shown that that confirms our answers in part 3. Okay. I'm probably not going to get through all of question 2, but it's essentially the same. We're basically, calculating two ways and showing that Stokes' theorem works, and we're showing it to be true in all of these cases. So again, you can find, so I've got this vector field, x onto I plus y onto j plus 1 plus x squared plus y squared k, and I'm going to, because I've got this problem, I said that you've got this pipe, maybe fluid is flowing up it, and then you've got this intersection with two pipes here. I'm not really sure how this would work, but say, you've got this space curve, and say we're looking at the surface where that intersects with maybe a pipe coming through this way and a pipe coming through this way, and they just fit into each other. And so, this problem, I guess it lends itself to cylindrical coordinates. So the first thing I'm going to do is transform the vector field into cylindrical coordinates. So, I do the same thing. I have it in x, y, z as x on 2, y on 2, 1 plus x squared plus y squared, I, j, k. And then I'm just going to use that same transformation. So I know x in cylindrical coordinates. I know y in cylindrical coordinates. And then I'm going to use that same transformation matrix. And if I do all that, I get rho on 2 in the rho direction plus 0 e phi plus 1 plus rho squared ez. So that's my vector field in cylindrical coordinates. And then again, I'm going to compute the curl in cylindrical coordinates. Oh, sorry. I'm going to compute it in Cartesian coordinates and then convert it. So for the first one, so differentiate 1 plus x squared plus y squared with respect to y. I get 2y I because the other one this term has no z. And then if I do minus, and if we differentiate the same thing with respect to x, I get 2x. Again, the other one has no z. And then when we do the last one, this term has no x, this term has no y, so it's just 0k. And then converting that into cylindrical form, I'm just going to do the same thing as I did when I converted the vector field itself into the cylindrical form. So we have 2y, which is 2 rho sine phi. We have minus 2x, which is minus 2 rho cos phi, and 0. And then we use the same transformation matrix from the first page. And I'm going to find that it's 0 rho direction minus 2 rho phi direction plus 0 in the z direction. Did anyone have any questions about that? I've sort of skipped over it just so I get through a little bit more of the question. And then I sort of combined questions, part 3 and 4. So basically, it's saying, like, this surface here, I mean, I didn't even draw it in my diagram because I found it a bit hard to draw it in, but so this surface here, I don't even know how to, I guess, write that out off the top of my head. It looks like an ugly surface to integrate over. So instead, we're going to use Stokes' theorem. So instead of integrating over this surface here, that's bounded by this red space curve, we're going to integrate over the two surfaces, this cylindrical one here, and then this one on the bottom as well, this disc here. So where S1 is the bottom of the cylinder and S2 is the side of the cylinder, we have so rather than computing that over that difficult, wavy blue surface, we're going to look at computing that over the sum of surfaces. Where S1 is the bottom of the cylinder and S2 is the side of the cylinder. So since S1 is at constant Z, we have that N1 is going to be equal to EZ. And since S2 is at constant rho, we have that N2 is equal to minus E rho, and that's just because so we've got pointing that way, and I think that's because of the right hand rule and this red curve there again. So I think you're meant to be trying to set out your assignments in the format that Michael Bryson has specified. So I think in yours, the you want to make sure you keep these questions separate, perhaps. I haven't quite looked at exactly the details of how you need to set them out. But so that's the curl I found in part 2, dotted with the normal vector, and I just get 0. And then on S2, that same thing, we've got a different normal vector. Oh, sorry, that's a minus there. And that's still going to be equal to 0 because there's no, the only component of the curl that has a non-zero is in the phi direction. So we just get 0 again. And then I guess this part is the actual part 4, where we just sum that up. But 0 plus 0 is still 0, so. And then the final part is we're going to confirm that answer that we just saw by, again, instead of doing the instead of finding that sort of that like the integral over the surface, actually I think part 3 was, I mean, you should, guess it pays to read the questions properly. Part 3, it was asking you to compute just this part and this part, and then I guess part 4 was, you know, doing the two integrals and summing them. Yeah. And then, so in this one, instead of doing this, the surface, like summing these surface integrals, we're going to just confirm our answer by finding this line integral instead. So that C was this R of t, which is given by cos t I plus sine t j plus cos 4t k. And then we need to find dr dt, which is just minus sine t I plus cos t j minus 4 sine 4t k. And we need to find f of r of t. So I'll get 1 plus cos squared t plus y, sine squared t. So this part here is just going to be 1, so it's going to be 1 plus 1, so 2k. And now we can find f of r of t dot dr dt. And I've run out of time, but if I dot those two together, I get minus 8 sine 4t. And then I will want to integrate it. So I'm going to end up integrating this over t, and if I solve that, I'm going to get 0, which is the same as I had before. But yeah, obviously in your assignment, you will need to write out those steps a little bit in more detail. Otherwise, you won't get all the marks. But I just wanted to sort of rush to the end and get the answers. Did anyone have any questions about anything I've covered in this tutorial? 2i. So I was, that was pretty brief there. You'll need to do a lot more working, like, multiply each thing out. But again, I just wanted to get through it all, cover everything.
Thank you, Catherine. Pleasure as always.
Thank you. And I'll try and get your assignments marked. Part 5, do you mean? Yeah. Again, it's sort of quite brief there. You'll need to show more working. Yes, I believe the final assignment is another in-class assignment where you'll need to submit all the questions again. But yeah, Michael should send out information about that as well. I just make sure you read all his emails. Cool. I'll talk to you again next week. See ya.